I didn't go back to the old book. I apologize. I just think, honestly, the problems in here are a little more understandable in terms of the depth. And the old book, there's nothing wrong with it, but it is. Those problems, at least in the sections we're covering, they're not easy. So here's what I propose to do. I'm going to go through really hypothesis testing, section 4-5, and I'm going to get into chapter 6 just for a bit. Now, these two things, I'll tell you what I'll hold you accountable for, all right? I have to do this just to introduce it. It's part of the coursework. I know in the summertime it's a little tough sometimes, especially with all the days off we've had. I don't know if we've missed our mark in terms of the class hours, but how many days off do we have?
That week and a half in June.
There were weeks where I had one class, and that's it. And I mean, that's really cutting into the core. So let me do this. First, I assigned some problems, right? Out of section 4-5, correct? All right. I want to go through this, and I'm going to go through that, and we'll do some problems. I'll do the exercises, but I'm not going to. What I want to do is make you aware of some things that are critical to understand this stuff. So in general, you know, if you're a manufacturer or anything, there's something really odd about what's being said in this section. And you claim that you have certain things that have a mean value of X, and they got a certain standard deviation of this that's known. Just assume it's known. And they say they're 95% confident the mean value will lie between a certain value. All right, 95% confidence that the mean value is going to be within certain values. Now, here's what they really mean, and I want you to just appreciate this. Let's use Gaussian statistics, okay? If you look at this for Gaussian statistics, if you have a mean value here, it means your probability density function is going to look like this. I'm just showing you what the PDF would be. And here I'm trying to be I don't want to clutter with any details that's unnecessary. Everybody follows me on that. Now, if they say 95% of the samples are going to be within, say, a value of delta X is going to be, say, 2 of the mean. I just call it delta X of the mean. All right? So what does that mean? Well, if I come out here, and I just want you to follow me on this. Here's the mean. Here's going to be X bar plus delta X over 2. And here it would be X bar plus or minus delta X over 2. And what I'm really claiming is 95% of the area of the curve is between those 2 points for the mean. All right? These are statistics about the mean. Now, you'll notice something. That's 95% confidence interval. Do you all follow me on this? What if it's 90%? This actually shrinks. It's less wide. Do you all follow me on that? Kind of anti-intuitive. 95% confidence interval is wider than 90%. That's why in the book, did anybody read through that section? 4-5? In the book, he says it's a bit paradoxical. Really, when you get a 99% confidence interval, you're out here and you're going to say, I'm 99% confident that the sample mean is from here to here. That's a bigger spread than 90% confident. It's counterintuitive. Do you all follow me on this? But that's what it means. Oftentimes what they say in the book is if you take 1 minus the confidence interval, that's more representative of how likely that value is correct. That's one of the things they state. Did you read this or not? Anybody read this in the book? Has anybody read section 4-5? If you didn't, I understand, but you're going to have to at least go through it one time in order to appreciate some of the questions I'm going to ask. You've got to go through it just to be familiar with the lingo. So now I propose to do this. All right, in general, and I put this up on the slides. The slides are excellent, by the way. Denny's slides really capture everything you need to know. When we're dealing with things, there are 3 possibilities. One is if we have a large number of samples, large n of samples, or small n of samples, and sigma and the mean value is known, right? Then we go right away and we assume Gaussian statistics and we use the characteristic function. But now, in general, now when we talk about, remember, when we talk about the characteristic function, we're always talking about something where it's normalized and we have a value z that is really going to be the value of x minus the mean of x over usually just the standard deviation. But when we're doing this stuff with confidence interval and everything, what happens, it's actually the standard deviation over the square root of the number of samples. This is the first one. Does everybody remember this, right? That's the first one. And this is still Gaussian. All right. Second one is, actually, I'll just break it up. That would be for Gaussian. And then for student t distribution, this means the n is of the order of small, right? And also that it's non-Gaussian. And really, the real standard deviation is unknown, but we know the sample standard deviation, and that's S for the sample standard deviation. I'll move out of the way in 1 second. And we know the sample mean, so we know X, actually X sample, I'll put it down here. So we know these two things, and when we know these things, we use the student t distribution. We go about, and I think he calculates, I think he calls it just t in this case instead of z, is going to be x minus x bar, and this would be the sample here, over s, that's this, over the square root of n. Now, the only way to see how this works is apply it to problems. All right. Now, do you all remember going through this? It's in the overhead. It's in the notes. This is not the best cut at everything, but you can look at the PowerPoints. I'm just trying to contrast the two. So if you look in the exercises, this is in section 4-5. If the first exercise, I think, is just calculating student t's value, I think, isn't it?
No, it's a certain type of bipolar transistor.
Oh, okay.
It has a mean current value gain.
All right, we'll do that one. I want to do these because when you see the theory in action, and if you want, you can just take a look at the PowerPoints and take a look at this is in the hypothesis testing, take a look at the three possibilities for what tables you're going to use. You're going to use large number of samples Gaussian, small number of samples Gaussian, or student t. Student t is if you don't know the variance, but you know the number of samples, okay? And I'll do it right here. So this is exercise 4-5.1. Go ahead.
Okay. You got a certain type of bipolar transistor is claimed to have a mean value of current gain of beta is greater than or equal to 225.
So beta, greater than or equal. Oh, this is, I didn't say this, but there are one-sided distributions that we have to worry about if it's greater than or less than. There are two-sided distributions where it's between two values, like the means within a certain value. It's above a certain value, below a certain value, okay? So hopefully we'll get to this and I can make this a little more clear by doing these exercises. So beta greater than 225, go ahead.
Yes, and then a sample of these transistors is tested. And
This is the mean value of the actual current gain, right?
Yeah,
and beta
yes.
is a symbol for current gain, I think. Go ahead.
The sample mean value of current gain is found to be 210.
All right, so this is of the sample is 210. Go ahead.
And then the sample standard deviation is 40.
Okay, S of the samples is 40. Okay.
And then if a 97.5% confidence level is employed.
Okay.
And then it's asking if the claim is valid if the sample size is 81.
N equal 81?
Yes.
All right. Now for this one, it's a little odd. but we're going to go through it. You with me? That's a fairly large number of samples, but we're going to use student t because we don't know the actual standard deviation. We know the sample standard deviation. So if you don't know the real standard deviation, you default to the sample standard deviation. Do you all remember that in the book and the slides? Okay. So for this one, the first thing, he's saying it's 95% sure that it's above that beta, right? Now, here's what I'm going to do. I want to go over here to the table and just draw this and show you what he means. So you get a visual picture in your mind of this. First thing, I'm going to just say, we don't know the standard deviation. We're going to use student t. Okay, that's the distribution function we're going to use. Now, after that, what does he mean? Well, he's saying if the mean of beta is, he's claiming he has a beta greater than 225 right here, and he's 95% sure beta will be greater than 225. Do you all agree with this, class? So that his mean value will be, which really means this. If you think about this, I'm trying to draw this in a way that's meaningful. If this is the actual probability density function of the mean value of beta, he's saying that the area over here, or 97.5, or 0.975 will be the area that I'm shading. That's what he's really saying. Okay? Now we're going to see if this is true. So we come over here, and if we have this right here, we're going to look down here at the student t distribution. Well, I tell you what, we can do this first. If this area, 97.5%, is greater than that, right? And you look at the student t distribution, the definition of the student t distribution, really, I think in the book he has ft of t is equal to the integral from minus infinity to t of the density function, that ft of t, the thing with the gamma functions, dt. That's what it says, right? In the book. If you look, I don't know, it's, if you go to the back of the book here, I'll show you where it is. I'll tell you the page number so you can look in your notes on this one. That's on page 436. And if you look there, he'll have the student t distribution. Now what we want is really, we don't want to integrate from here up to here. We want 1 minus that. Don't you agree with that, class? So what we want is 1 minus f, you'll get the hang of it in a second, of t is going to be equal to 0.9, what is that, 75, right? Now, can everybody follow me on this one, class? All right. So when we're looking at this, did you follow me?
Yeah, I'm just trying to see if I can do it in the calculator.
Oh, for student t? I don't know if your calculators have that. They probably do, but it may be in terms of gamma functions, and you have to program. But you might have student t. If anybody, if you just look it up, if you have a modern calculator, this is fairly common.
Would it be this T?
I don't know.
Yeah,
If you're asking me,
that's what I was trying
I have
to
no
see.
clue. All right, so let's see here. That means, all right, so I have 1.975. Actually, I don't. Hold on. Let me do it this way. I'm doing this wrong. I should say that if I take this and I have 1 minus 0.975, it's equal to ft of t, and that's equal to whatever the value is. This is 0.0025 is ft of t. I believe this is right. I didn't do this one, but you can tell me the value of t that makes that true. If you look in the tables, you can tell me that value. Hold on for once.
Say 436.
Give me 1 second. Go ahead.
So you got 0.975.
No, we need f of t is 0.0025.
Yeah, I don't know how to read this. I don't see a 0.0025.
Oh, you know what else? I got to be careful of this. This is the number n is 81, so 1 minus that is going to be the actual degrees of freedom for this one. V is going to be equal to 80. Let me just see that for one second. I'm sorry, I should have done this one. Let me just see this for a second. This is, oh, my bad. Here. My bad on this one. The problem is, I'll tell you what the problem is. We got a sample size of 81. That's above 30, so we default to Gaussian statistics. My bad on this one. Let me go ahead and do this. I think I mentioned that the magic number is 30. If you have more than 30 samples, regardless of standard deviation, not use Gaussian statistics. It's there, so just write that down somewhere. Here we have n greater than 30, so we use Gaussian. All right, now after that, after that, what we have to do is for Gaussian statistics, they want to, and I'm just going to draw this up here so everybody understands this. I have a beta value of 225 equal 225. And what I want to do is make sure that this area, now I'm going to get this right, I think. PDF, this is what the claim is. And this is the PDF, that this area right here is equal to 0.975. All right, the total area is 1 under the curve. I'm sorry, this is what the claim is. This is the claim. Now, what does that translate in terms, what does that translate in terms of the normalized value? Actually, what I'm showing you here is a value would be. But now, if you think about really the way we do this, we normalize everything, and we talk about a value of ZC here. And remember, the way we get it is this. We say, now I'm going to go ahead and I'll say Z, or excuse me, my bad. I want this area to be equal to 0.975. So if that's the area, and I think about this for a second, I want to make this clearer, so I'm going to try to go over here and use this board. And let me even say this. This is the claim. With hypothesis testing, you're going to assume the claim is true. That's called the H0. Or it's false. That's H1, which is the opposite. It's not. So we're going to see if this claim is true or not. But first, we need this value of ZC. Now, remember, in general, the way we got it, we could use the Q function to find this value. You all follow me in this class? Or you can use 1 minus the characteristic function. All right? So if you look at this area right here, if we take 1 minus the characteristic function's value and of this, which is, I'll just call it ZC, that has to be 0.975. And if you look at this, that means, hold on for 1 second. For this one, I got to do this right. So for this one right there, since this is going to be the normalized value here, I know that either the Q function of ZC has to have a value of 0.975, and we can look up that value, or this should be 1 minus the characteristic function of ZC. It's going to be that. So let's see here. We're going to have ZC characteristic function is equal to, and what is that? 0.025. And what is ZC here? Because I can't. You know, this is the characteristic function. It's the tables. It's at the very end, right?
Is it the Q function?
Well, you could use Q if you wanted to, but this is the characteristic here. If you take a look at the Q functions, you got a value. See, that's 0.5 here. Wait a second. Characteristic function.
Would it be between here? Well, no, that's 1.8. So.
No, actually, the problem is
between these two.
You've got to take 1/2 and subtract. I mean, it's basically, to do this, if that's the value right there, let me just see if the Q function has it. They may not. They may, because it starts at 1/2 for the characteristic function. If we find this value for 0.1, we'll take, let me do it this way. Let me try to explain this. I know that right at the mean value, this is going to be 1/2 the area above. And that means the area below this is going to be 0.975 minus 1/2 is going to be the area below the mean value. And that's this area here. So if I take that, no, we should just be able to do 0.975. Here, I'm sorry about that. I'm messing this thing up, and I'm sorry. So again, this is a Q function.
So it wouldn't be between these two.
Well, these start at 0.5 here. So it's 0.50, 0.501. I mean, see this? Like this is the values of x, and these are the values. We want it to be 975 is right about here. So it's 1.96. I think this is right. Let's see if we get this. So, despite all the errors I'm making, that's an argument of 0.9. Say that again. 1.96, right?
Yes. 1.96.
Yeah, that's going to be the z value that would give it to, and I'm not saying this exactly right, but if this is the mean right here, whatever it is, normalized mean, which is going to be, I'll just call it x normal here. This is how far down it is from the mean. That's what it means. So it's got to have a value of this down from the mean, or the actual value is going to be the mean value of the transistors of the actual the measurements minus that. Let me try to do this right. And anyway, for our measurements, what was the standard deviation based on the measurements again? And I'm sorry about that. Go ahead.
The standard deviation, somewhat for the sample standard
Yeah.
deviation, that's 40.
And the mean?
The sample mean is found to be 210.
210. That means when we take a look at this, if we get z now of this, it's going to be, sample mean is 210, actual claim mean is, what was the claim mean again?
He just says that it's greater than 225. So I don't think it really gives us a mean value. He's just,
So it's
claimed to have a mean
225.
that's greater than 225. So I don't even think we have an actual mean.
Yeah, well, it's greater than that. That's the claim. And this is going to be over the sample mean is 40. And how many samples again? 81?
81.
Over 9. So what is this going to be? That's 15 plus or minus 15 over, or times 9 over 40. I don't know what that is. Can you just tell me this? And I'm sorry about this one. I wish I would have done this entirely. What is it?
3.375.
Yeah. And that's the right z value.
Pardon me?
That's the right z value according to the answers.
This should be the value also in there.
That doesn't matter.
He doesn't have a 1.96 anymore.
Well, this is the z value for this, right? Well, this is much greater. It would be actually the negative of that, less. So this thing fails because the sample mean was 210 and the actual claim mean was 225, right? What was the sample mean, 210 or 225? I'm sorry.
210 was the sample mean.
And the claim was that it is 95% sure above 225?
Yes.
Then that fails. I mean, but I'm not saying this in a way that's making it easy to understand. I'm going to try to smooth this thing out. But the whole idea is this, and I apologize for not saying it clear here. I'm trying to use the characteristic function and the student and the Q function or the student T function to get the values, but I'm trying to show you a picture of what really is going on, and I did a bad job there, and I'll be the first to admit. Let me try this again with, is there another part? There's student T is the next part, right?
Yes, student T's next part is for B. It's just if the sample size is 16 now.
Well then, now you're going to use student T, but let me jump to the next exercise. I'll clean this one up in a second. I think I did this next exercise, but I've done the problems. This one, for some reason, the whole problem I'm having is using that characteristic function when I don't have to subtract 1/2 or really worry about that starting at zero in my calculator or in MathCADS, and I should have done that. Let's do the next one. I'll try my best here.
Okay. This is 4-5.2.
exercise. Go ahead.
All right, you've got a certain type of bipolar transistor is claimed to have a mean collector current of 10 milliamps. So this is saying that the mean is 10 milliamps. A sample of these transistors is tested, and the sample mean value is 9.5 milliamps. And then the sample standard deviation is 0.8 milliamps.
Oh, wait, sample mean is that, right?
Yes, the sample mean is 9.5 milliamps.
And
The sample standard deviation is 0.8 milliamps.
okay, go ahead.
And then your confidence level is 97.5%. And then is this claim valid if the sample size is 81?
All right, now we got n equal 81, and read that. He's saying that the mean collector current is 10 milliamps.
Yes.
And it's and what did he say about the 97.5%? Is it between or above or
He
what?
just said if a 97.5 confidence level is employed, is this claim valid if the sample size is 81? But I don't think he says if it's above. It just gives you a mean value,
All right,
tells you the sample mean and sample standard deviation.
I'll try to do this one a little clearer. I'm assuming he's talking about within 97.5%, sure that it's within 10 milliamps. So I'm going to first drop the PDF of the claim, and I'll put it even down here. This is the claim here. So here is the I collector current mean. This is the claim, and he's saying it's going to be 97.5% are going to be with. You better read that again. I'm thinking this doesn't make sense if it's within that range. Go ahead.
You have a certain type of BJT. It has a collector mean of 10 milliamps. And then a sample was tested, and the sample mean is found to be 9.5 milliamps. And the sample standard deviation is 0.8 milliamps. And then if a 97.5 confidence level is employed, is this claim valid if the sample size is 81?
It doesn't say with above, just equal, nothing? Or is he right about? Doesn't say above, just within?
I don't see anything saying
All right,
above.
so if you assume what I think he's saying is this, and I don't like it. He's saying that the collector current has got a 97.5% chance of being 10 milliamps. And that's about what he's saying here, which I don't like the wording on this. So now there's going to be a value, a minimum value here, and a maximum value in the spread. And it's here. I'm going to try to do this. I'm not sure I like the wording of this problem, but, and this is the mean value of C. So here's what I really have to do. Once you normalize the values, you know, we always normalize things. All right, we're assuming we've got, how many samples? 81, so we're going to use Gaussian statistics. So now I've got to figure out that, and that means, technically speaking, I have 0.975 would be equal to the density function. This is the probability density function of this, which is going to be Gaussian f of IC DIC. And it would go from, and this is the value I need, from the mean value of I minus, and this would be K times the actual standard deviation. Well, I'll just put minus delta I to I here plus delta I. I'll call delta I over 2. No, I'll just leave it as delta I. We're going to see this in a second. What is this really? Well, this is the characteristic function above, so it'd be, if I evaluate the characteristic function at this value, and actually it's, now we're going to normalize and do it with a normalization. I'm sorry about this, but so now I'm going to use the characteristic function. So I'm going to say what I'm going to do at this point is I normalize, and I have this being equal to the normalized density function. I'm just going to write it down one time, and I'm not going to labor it. So that's equal to 1 over the square root of 2 pi here. Sigma is going to be 1, and it's exp to the minus, and you can call it x for all, x squared over 2 dx. I'm saying that's going to be from some minus delta x to some plus delta x. That is what he's asking for. And we know the characteristic function, what's normalized, goes from minus infinity to that point. So what we're going to end up doing is say 0.975 will be equal to, and here I'm going to have the characteristic function of some, and this will be the argument ZC because it's going to be normalized, minus characteristic function of minus ZC here, and that's really going to be the characteristic function of ZC minus the quantity 1 minus the characteristic function of ZC here, because this is 1 minus this is equal to the characteristic function of minus ZC. So that's going to be equal to 2 times the characteristic function of ZC minus 1 and equal to 0.975. Just realize the only thing I'm doing here, I'm trying to get this to a point where I don't have to worry about the values that I'm going to have to calculate for these functions to be outside the realm of where the table is. This is the reason I'm putting 1 minus this. So I get this value, and then I add 1 to it, and I get 1.975 here. And then I divide that by 2, and now I get the characteristic function of ZC. Can you just give me that value? 1.975 by 2? That's 0.9875. All right. So this one you should be able to look up. If you look at the characteristic function's value of 0.9875, it'll be 0.98, and then you can look up on the top. I think they'll have 0.01, 0.02, and so forth. Can you find this value, 0.9875?
Is this for the student T or?
No, this is the characteristic function. See, the sample size is 81. This should do it, I hope.
2.24.
Okay, so ZC is 2.24. Is that, can anybody confirm that? Is that right? Looking at the tables? I'll trust you on that one, but.
I might be wrong.
Huh? What?
I got the same thing on my calculator.
All right. So that's the value of ZC that we're using. This is his statement. Now we got to find the actual value of ZC. All right. So in our statistics, we have these values, right? It's large. So now we take a look at this, and now we're going to calculate the Z of this, you might say, the normalized argument of this. Do you all follow me? So when we do this here, and I'll just call this Z prime because it's going to have to do with the actual measurements. Now I have sample mean is 10, right? Measured mean is 9.5. So that's really 10 minus 9.5. And the standard deviation is 0.8. So it's going to be 0.8 over the square root of n, which is 9, right? Let me just see what this comes down to. So I got 0.5 times 9 over 8 is 0.8. Can you give me that value?
5.625.
Is it 5.625?
Yes.
And our value, this is outside the realm. All right? It's either greater than or less than if it's double-sided. Does he have?
No. He got 1.96
For what?
For his ZC.
For this? Or for this? Is he got that for this ZC?
No. For his Z, he got -3, and his ZC, he got plus or minus 1.96.
Wait. He got -3 for what?
He got -3 for just like his Z value.
That's this value, right? Here. How did I? Oh, no, it's 81 samples. Square root of that is 9, right? Is this, did I do something wrong here? That's 0.5, right? Times 9. 4.5 over 0.8. He got 3 for that? I mean, you can switch the signs. That doesn't matter. How did he get 3? That doesn't seem right.
Is that just regular Z or ZC?
This is for the samples. It's Z of the sample. And Z of the sample, if it's within the bounds, it passes. If it's outside the bounds, it doesn't. Unless he used one-sided, and he's saying at least that or greater than that. But I'm not actually sure about this.
Okay, I'm not sure either.
I'm sorry, these exercises I should have done in great detail. I did the problems, and I'm going to tell you right now, because these things I'm fumbling because of my lack of understanding of exactly what they want here. Take a look at problem 4.51. I want to run through these, but I'll try to be a lot more clear. And I'm sorry about this one, but I'm not absolutely sure what if he's asking above that or equal to that, and he does not. There's nothing in the solutions about this. By the way, I posted all the solutions for the entire book on OneNote. I don't know if you saw it, but the entire book, not just chapters that we covered. Let's try this one, and then I'll get to what I need to do today.
All right, 4-5.1.
This is problem 4-5.1. Go ahead. I'm sorry.
The resistance of coils manufactured by a certain company is claimed to have a mean value of resistance of 100 ohms.
100 ohms, okay.
And then a sample of 9 coils is taken,
N equals 9. Go ahead.
and it's found that the sample mean is 115 ohms.
All right, so R of the sample mean is 115, right?
Yes. Yes, and the sample standard deviation is 20 ohms.
All right, really? Okay, go ahead.
And then for part A, is the claim justified if a 95% confidence level is used?
All right, so he's using 0.95 here. And really, I'm going to do something here. Remember, when we do the characteristic function, before I do anything more about this, we always say the characteristic function, or the arguments to that, and this is, by the way, this is a claim, so it's within these bounds. And I'll try to put this up here and then say this in a way that's clear, I hope. Here's what he's really saying. This is the probability density function of R mean, and he's saying that if we take a look at 100 ohms, so R, the claim is if this is 100 ohms, that his density function centered there, and the value of the mean, he wants the 95% confidence interval here. So what he's really saying is this: we've got to find this out, and then we're going to see how this whole thing works in a second. So I know this is 0.95. Now what I'm after, this is the normalized thing I'm showing you in a second. I mean, this is really, sorry, not normalized. You all with me on this one, class? That's not normalized. And we know we're going to have a lower value that's going to be R bar minus delta R over 2, and an upper bar here that's R bar plus delta R over 2. You're going to see these things simply become something he calls K times the standard deviation, but I don't want to do anything more about that yet. What I really want to do is focus on how to translate this into something meaningful. So this is his claim. Now we take all that and we put it into a normalized value. So the first thing we're going to do is realize when we get Z here, ZC, it's going to be associated with that. That's actually going to be, always it's going to be X minus X bar. Down here, it's the standard deviation divided by the number of samples. Here we have a sample standard deviation of 20, 9 samples. So this is going to be, so it's going to be, maybe I should just put that down there. It's S over the square root of N. Now, what I need is this value right here, but I'm going to just leave that here for now. We'll get this value in a second, but so this is X we've got to figure out, which is really going to be my delta X over 2. X minus an X bar.
Would that be 100?
Actually, it's this is going to be 115 as a sample mean, so it's 115 here minus this X bar, which is 100. I've got these reversed. It should be over 20. That's the square root of 9, which is 3. We'll get to this in a second, but that's, what is that? 15 over 20 times 3, so that's 9/4. That's about, or 2.25. So it has to be within, once you normalize everything here, for this claim to be true, let me step back. That's the key number we're going to measure everything against. Now when we take a look at what he's claiming with his distribution function, remember this is going to be normalized now. We have to figure out this. This is going to be normalized, and this is the distribution function, and we have to figure out if this right here is normalized, it's the normalized z, what these bounds are here and here for z and zc and minus zc for 0.95 or 0.95 of the area. Total area would be 1 under this curve to lie. So that's what we have to do. That's what I'm really saying. So here, if you have 0.95, that's going to be equal to, technically it's equal to the characteristic function of zc minus the characteristic function of zc here, and that will be 0.95. Here, that's the characteristic function. I'm going to write this down one more time. Minus 1 minus the characteristic function, that's a minus zc, sorry, of zc here. And that's really going to be 2 times the characteristic function of zc minus 1 is equal to 0.95. Just help me out here. And that's going to be 1.95 over 2. Over 2 would be equal to the characteristic function of zc. You all with me on this? I'm trying to just get this thing in something we can measure. So what is that? 0.975. And now you got to look that up and tell me what zc is, because look up where the characteristic function, this is the characteristic function is 0.975, and tell me what that value of zc is.
The 1.96.
Say again?
1.96.
Yeah, that rings bells. That would be zc. Now, if you take a look at that, that's 1.96. Here's the thing. Once we normalize that stuff we just did over there, if it's not within 1.96, if it's outside that, then it fails. Y'all follow me on this? This is the thing. You're trying to use the claim to create a density function, then normalize it, and you've got to figure out the upper bounds on this z value, the normalized value. And if, and this is within a region, if the value of z that you calculate, once you do the normalization over there for the measurements, if it's within that range, it passes. If it's outside, it fails. So it should fail. It's 225 is outside. Does he have this there?
He doesn't have the answer.
You got the solutions.
No, it's not the case.
What does he have?
225 is right. That number needs to be 2.306.
What did we do wrong? I mean, it's 95% confidence interval, right?
You use student T instead of a...
What?
You use student T here instead of the one.
Oh, gosh. That's right. There is no standard deviation. It's a measured standard deviation. There's only 9 of them. Now you got to use student T. I'm sorry about this. I'm messing this up, and I apologize to you. You're right. Now, here's the deal. He didn't give me the standard deviation. It's based on measurements. If it's based on measurement, small sample size, you use student T. If it's based on measurements, but he gives you the standard deviation, the actual, then you use Gaussian, even if it's a small. And if it's a large number of samples and they have in the Gaussian distribution, obviously use Gaussian. So for this thing, we got to use student T, and I apologize for this. This would be true if we could use Gaussian statistics, but for student T, it's going to be the same deal again, only one. So instead of this being the characteristic function, now this becomes student T distribution. I think he has it as f of t in his book, right? All this stuff is going to carry out just like before, only now you're going to get this. You're going to get the student T right here, f of t equal to that, and now he's going to have a t value here. So what t value gives me 0.975 for the actual, in other words, this function is going to have a value of 0.975. What's the t value if you look it up?
It's 2.26.
Well, is it looked up though? I just want to make sure it's right.
Yeah, that's what I'm looking at right now.
Yeah, 2.262
All right, 2.262, is that right?
for 0.975. And what's the V on?
That's n minus 1. So n was 9, so it's 8. Look at n equal 8.
Oh, then he gets it. It's
Yeah.
2.306.
Yeah, so it's 2.306.
Yes.
All right, now that's greater than 2.25. Do y'all follow me on this? I'm sorry, greater than, wait a second. That's 2.20 or 2.306, and that's 2.25?
So it falls within 2.3.
Yeah, that falls within it, right? Isn't that what he has?
So,
Yeah, I'm
so therefore
sorry.
his assumption was correct,
Yeah, I'm sorry, buddy. So
or his claim was correct.
if after you do the normalization of the measurements, after you take care of the measurements themselves, you use the standard deviation, the measurements, normalize it, okay? If that value is less than or equal to this value, hypothesis passes as it is. If it's greater than that, if that was like 5, then it would fail. I'm so sorry I did that. Okay, go to the next part of this one.
Okay, and then is the
I'm just
claim
not having a good day.
is the claim justified if a 90% confidence level is
Oh,
used?
this is the crazy part. All right, this is crazy. So 95% sure, or the area from here to here, 95% sure our mean value will be within these bounds. Now he's going to say, where's the 90% confidence interval? This is a little, it's going to be less than this, right? You all with me on that, class? So now we leave that alone, and we come over here, and I'm going to just do this right here. Remember, the only thing I'm going to do is, only thing I'm going to change here is instead of 95, now it goes to 90. So if I have 0.9, what does that really mean? He's saying if I integrate, and this would be the student t distribution function, and this would be from some minus t to plus t value. I want to see if it's 0.9. That's what he's really saying here. Think of student t just as you did the characteristic function. It's analogous, only now it's going to be for things we don't know the actual standard deviations, all right, and we have a small sample size. You all with me, class? Just please. So what is this? That's 0.9 is equal to, and here it's going to be f of student t of t minus f of student t of minus t. This is the same deal with the characteristic function. This I can replace as 1 minus the positive value of the argument. So it becomes, really, this is going to be f of t minus 1 minus f of t. And Zach, you correct me if I'm going off track, but I think this is how you should do this one. That's 2ft of t minus 1 is 0.9. And that means f of t, you're going to have to look this up. ft of t here, that's 0.9, is going to be,
It's 0.95.
yeah, 0.95, so it's 1.9 divided by 2. Isn't that right? So 0.95 is f of t, and what t value is that?
It gives 1.86.
Did you look it up? 1.86, is that right? Now, remember, that doesn't change. We've got measured data, we've got the standard deviation, we know the numbers, it's a small number, we use student t. If it was over 30, we'd go to Gaussian, or we'd use characteristic function. I guess that's what I'm really trying to underscore is the decision making here. That stays the same. You can see that that is outside this range, all right, because it's plus to minus t, and that means it fails. It should say that. All right, but that should be, I'm sorry, I'm not being more exact about this. I just don't want to throw up PowerPoints. I really don't. Okay, let's do the next one. I'm going to put a few things up in a second. I just want you to know this, really, when you get out there in the job world, and they're talking about yield rates and all this, you got to be real careful. You look exactly what they mean. The confidence interval, as defined in this book and in statistic, does not mean if you're 99% confidence interval, if you're within it, it doesn't mean you're within the 90%. It's less likely, which is irritating to no end. So normally what they do is try to find a figure of merit that indicates the larger the value, like 99.999% within there, is an indication of how good it is, all right, rather than where you have to interpret all this stuff.
No, sir, I'd leave all that stuff because the next problem is a repeating of that, except your sample size has changed.
All right, I tell you what, I'll put it over here. I'm glad you said that. What did the sample size go to?
It went from, it's at 50 now.
All right, 50's large.
And then the standard deviation also changed from 20 ohms to 50 or to 10 ohms.
All right, so the claim is R bar is 100, right? And this is 4-5.2, right?
Yes.
And that's a problem. And is the claim still 90% or 95%?
Yeah, we're just going to repeat part
Okay.
A and B. So claim of 95 first, and then a claim of 90.
Now go ahead, sample size is what?
50.
50, it's large. Okay, go ahead.
And then the sample mean is still 115 ohms, but the sample standard deviation is 10 ohms.
Sample mean 115 ohms and sample standard deviation,
Is 10 ohms.
that's 10 ohms. Okay, now go ahead. Now what we need to do, I want you to just follow me. We're not using student T now, right? So what I'm going to do, like I did before, first I'm going to find out the normalized value of the Z of the sample, or of the T of this, or sorry, Z now, because we're doing Gaussian. So for this one, the value of Z here is going to be X minus X bar over standard deviation square root of N. Here, we're going to look at this. The mean is 100 and it's 115 measured, right? So 115 minus 100 on top. This is really just the difference in the measurement mean and the claim mean. That's all it is. And since it doesn't matter if it's plus or minus because it's within this range. So it won't matter. Down here, the sample mean is 10. That's small. And the number is 50. So it's over square root of 50. And what is that? That's 15, right? Divided by 10 times square root of 50. So that's 3/2 times square root of 50. What's the number here?
You got 10.61.
That's large. All right, so that's what we get based on the sample statistics. That's, to me, it's very significant. Okay, now back to this thing. Now we use the statistics I started with. We use characteristic function. I'm going to go over here and do this real quick. So the deal with the characteristic function, it's based on Gaussian values. We normalize that. All right, so what we really need to do is, it's 0.95 is the first one, right?
Yes.
Now we're saying we got, once we normalize, we're looking for the values here and here of ZC, minus ZC, and ZC, so that 90 or 0.95 or 95% of the area is within these bounds. That's the only thing we're looking at. We don't have to worry about degrees of freedom like you do with the sample T thing. So over here, I say, well, that's equal to the characteristic function of ZC minus, and this is the characteristic function of minus ZC. I'm putting it down on purpose so at least it sticks with you. Now I'm going to replace that with 1 minus the positive ZC. So this becomes 2 times the characteristic function of ZC minus 1 is equal to 0.95. Take the 1 over here, I have 1.95 over 2. We just did this, I know, but I'm redoing it. And that gives me a ZC value, is it 1.96? But this is actually what, 0.975, isn't it?
Yes.
And then give me ZC for this, we did this earlier.
It's 1.96.
1.96, that's normalized, right? Unless we did something screwy, that's way outside that realm. Does he have these values, by the way?
That value is 1.86.
Oh, is it 8.6? Can you check that?
I got 1.962. I don't know why I guess.
He probably just typo. He probably just messed up. But it doesn't matter, that thing's way up, right?
Yeah, it still fails, but
It could be, people are human, they make mistakes. 1.96 is the actual value, and 1.96 is much, much less than that value of 10. It fails. Now, next part of this, 90% confidence interval?
90%.
All right, so for 90%, same deal right here as we did, only this becomes 0.9. Follow me on this, class? This is the weird thing about this, right? So that becomes 0.9. This goes down to 0.9. This is 0.9 or 1.9 over 2, or this becomes what? Put it over here. We did this earlier too. Now we get, that's going to be instead of 0.975, that's 0.95 is equal to the characteristic function of ZC, and I don't know what that is. I remember doing this stuff. What was it?
Got 1.65.
Is that right?
Yeah, that's what I got too. The book says 1.397. Where he gets that from.
Is he doing this
He doesn't even do that, he just puts a number.
for ZC? What am I missing here?
It still fails either way, but I don't know where he gets that number from.
1 point what?
1.397.
And what's our value?
1.65.
I gotta see this. Something's goofy. Just let me see that solution. Is that the right problem? Well, he's got the right value for normalized measurement values at 10.61. Is he using student T? It can't be. I mean, what's our sample size in this one? 50. No way. No, that's Z. That is the characteristic function. I don't know, but there's something wrong about that. It fails no matter what.
Yeah, it feels either way, but I don't know where he got that number.
Neither do I. All right. So in fairness, for the final exam, I will not put a confidence interval. Just because I fumbled this too much, all right? I want to do one more thing, all right? Just bear with me, and I'll get to the thing. I wanted to do this, and this is in chapter 6. You all have access to the slides, right? That I put up there? This is Tom Denny's slides. Let me just try to do this and make sense of it, because you at least should be exposed to this if you paid for, if you're taking this course. And I think we had too many days off to do justice to some of this stuff, but I'm gonna do my best. When I do these problems, by the way, if I pull up MathCAD, I don't have to do all this adjusting of the characteristic function. I can look up the value. If I want the value of any of these things in MathCAD, I don't have to mess with tables. I just punch it in, and most of the stuff that I was doing, I was fumbling around, had to do with the actual values of how to determine the value of the characteristic. If you had the value of the characteristic function, what is Z? Because they don't get negative. They don't have values for less than 0.5 for the actual characteristic. All right, this is chapter 6, and I think I put these slides up, but I will if I didn't. Are they not up there? Bear with me, they will be in a second. So for this one, I'm going to just say this. I realize there's almost no time left, so I'm just going to get to the point. You all know what convolution is, right? You remember when you convolve two functions together, you're really going to multiply, or anything together. Whenever you convolve things, it's multiplying and then shifting and looking at the area. All right, and now correlation is the same thing. Have you had correlation before? We talked about that in class a little bit. Correlation and convolution are very similar, but correlation tells you how close something agrees with something else. And there's autocorrelation, that's self-agreement. Then there's cross-correlation. Now, in his book, and in the book I'll describe this. When you take a look at what's called the autocorrelation of a function, see this R of X thing? I need to at least give it to you so you've been exposed to it. It's taking the functional value. Now, it requires a data record. You can't do this unless you have recorded data or the history of data to do this. You can't do this in real time. You follow me on this, class? You record the data. Then you take the value of a sample at some T1 and value sample at T2, and you're going to find this value. What they really do is take the value at the difference between these two times. It's called the autocorrelation function. Has anybody heard of this before? So don't worry about T1 and T2. That doesn't matter. It's the difference in T1 and T2. So they normally say it's the expected value of X of tau times X of T plus tau. And they'll look at that as a function of tau. All right, so he's saying that if you have X of T, then the autocorrelation of this thing, and it doesn't matter what kind of signal this is. It could be a noisy signal with data in it, doesn't matter. But when you do the autocorrelation, the signal multiplied by itself and the expected value, the greatest value is always at 0 when there is no difference in the signal, because then you're taking the expected value of the square of the value. That's as large as it's ever going to get. Y'all follow me? If the signal x of t was sinusoidal or cosinusoidal, then you come out here and based on the period, every time there was a period, you would see another spike, and stuff like this. So, and he's just giving you 2 examples of this. I don't really care about that or that. This is the real definition we use right here. And I'm just making you, the autocorrelation function is the expected value of any signal times that signal plus tau. And you'll notice tau is the difference in the point of measurement of that signal. Now, what does that really give you? It gives you a weight of the similarity of those 2 signals with a certain time difference. And it's very, very important. When you take a look at people that play the stock market and stuff, they'll take things that affect stocks. I'm going to just say this. Say price or Pentium chips and Pentium stock. Whenever a new chip comes out, their stock takes a bump. It goes up because they expect this is going to be used so there'll be more sold, more profit. And you take a look at Pentium computer chips and then say computers that use Dell. And if you correlate the stock prices of Dell computer to the actual value of stock prices of Pentium. By the way, this is an interesting thing. We published a paper on this. I did this with a grad student, and we used something that was called a genetic algorithm for optimization to optimize profit. The kid's probably a billionaire by now. Anyway, what we did is this. I mean, what really happens is this. If you looked at that versus tau, versus the difference in time, you would find that all of a sudden, because it's, I mean, Dell computers use Pentium chips. Do y'all follow me on this? So when the stock price of Pentium goes up, all the things Pentium affects is going to go up at a certain length of time. So if you look at that autocorrelation and then 2, 3, 4, 5 weeks later, all of a sudden the autocorrelation function gets bumped way up there and it comes down. It tells you that if you see Pentium chips come out, buy Dell computer stock at a lower price, assuming other things are not affecting it. And then as soon as that Dell computer price goes above a certain threshold, and in other words, your profit margin, you find the expected value of profit, and you want a 99% chance you're going to make a fair profit kind of deal, then you put a sell order in. Now, if you haven't never done stocks, you don't know exactly what I'm talking about. Put a sell order in and just sell it. So you get a profit. That's literally the game. All right, I'm not doing anything to help society. I'm helping my wallet, but that's really the game these investment houses play. And that is using something akin to the autocorrelation function. In the simplest sense, it is the autocorrelation function. That also has to do with yield rates and transistors and many, many other things. One last thing, I know, I'm just trying to make sure you see this. This is an easy set of problems, 6.1 and 6.2, and I didn't get to my other stuff, but so be it. At least I mentioned the correlation function and its benefits. And I got to say one other thing. What you don't realize, most people are blind to this, that as engineers, you have all the tools to do extraordinarily accurate prediction of the market, barring wars, barring trade centers blown up. If you exclude those, your ability is every bit as good as almost any of these other guys. As a matter of fact, did I tell you the story about the guy who called me about grad school? Who was working on Wall Street? They want people that are engineers, bright people of sound mind that know how to make good decisions to do the modeling. But anyway, I'm going to say this. I am not somebody that plays the market a whole lot. I used to do this stuff, by the way. And it is fun, but you got to put a lot, you can't let one day go by and relax, if that makes sense. Because things can get bad in a hurry. If you got a whole bunch of money wrapped up in a variety of stocks, and you don't keep an eye on when you sell and buy and sell all the time. I lost $10,000 one time in the Chicago's future trade, and I will never, ever, if I play this, I play the game for real, and I don't take a day off. Go ahead. Final exam material. Somebody might be curious about this.
Just 1 or 2 people.
Okay, so I will send something out about the formulas, because you're going to ask me about that. I'll give you the formulas you get.
I was going to ask if we could possibly make a form.
No. I will make it for you. I'm that kind of guy. And I always try to go an extra step to please you. So I will take care of that, but I'll send it to you so you have it. I'll send you the ones you get. And then what I'll do is this. I'm going to say, well, you're going to get all the stuff from the beginning of the course to the last. I'm not going to put Venn diagrams on there. Hear me on that? No Venn diagrams. But think of the problems that have entertained me. Think of Merlot, think of Cabaret, think of Zinfandel, and probably think of beer too or what. Think of those problems, all right? Y'all follow me? Bernoulli stuff, I'll give you the combinations versus permutations formulas. Think about the homework problems and quizzes. So if I was sitting where you are, what I would do, with the exception of Venn diagrams, go through and look at the statistical stuff we did with the probability mass function, that's discrete values, probability density function, conditional probability, and then take a look at the stuff with correlation. I mean, this is kind of a no-brainer. All right, there are probably going to be 5 to 6 problems, probably 6, but don't hold me to that, and there'll be multiple parts, just like the quizzes. The quizzes are the best guess or estimate of what I'm going to do, and I feel very bad I didn't do a much better job on this. I'm not going to quiz you on that because of that, or autocorrelation, but you at least need to hear me say that word. And I'll tell you one other thing. Your next logical step is communications, right? When you take Jitendra Tugnate, communications, he will do things. He's an information theory specialist. Information theory is just statistics. It's probabilistic statistics of events in the real world. Now, natural things are great because they're Gaussian. Unnatural things have all sorts of skewed statistics. All right? I mean, but he's very, very good. He's very smart. But you're going to have to make sure when you get in his class, don't take a couple of days off to go just, I don't need to worry about it. You can get yourself in trouble. You'll learn a ton. And he does use statistics. I mean, the stuff we're doing in here, a lot. Okay. If you have more questions, I'll stick around.
The